We have seen since now how we can use the statistical inference to get some information about the probability distribution about an unknown variable using the observed data. Now let's use those concepts to develop some statistical tools that are often used in data science projects. So when approaching data, the first goal is to understand it better. And we can do it only looking at it. And how we can do it? We can do it using statistics. The typical tabular data can be interpreted as a collection of random variables. For example, here we have 6 columns and 5 rows. This table can be then interpreted as 6 random variables, the columns. So there would be 1 random variable for the age, 1 for the job, and so on, and 5 observations for each random variable. But as you can see, not all columns are the same. The age is a numeric admits a numeric values. The job doesn't. The housing is a sort of Boolean column. Admits only yes or no values. So let's study in detail this table and the type of random variables we could encounter when studying tabular data. We can find 3, we can say 2 or 3, depends on the definition, type of variables. We have the numerical variables and then the categorical variables that can be defined in binary categorical variables and the multi-class categorical variables. So for example, here we have that the age and the balance are numerical variables. The marital and the housing are binary variables because it's yes or no, married or single. There's no third option. And the job and the education is a multi-class. The job could be services, management, blue collar, unemployed. The same for education, primary, secondary, tertiary, and so on. So that we can encounter these 3 types of variables, 2 or 3 types of variables. Numerical variables are generally treated with continuous distributions. For example, even the age is expressed only in years. Generally speaking, we refer to it as a continuous variable, since the time underlying the years is continuous. Then let's move on to the right. In the categorical variables, generally, but especially multi-class, we intended them as with discrete distributions. For example, the education is a discrete distribution with, here we can see, 3 classes. The binary categorical variables are a particular type of categorical variable that can be described with a particular discrete distribution, the Bernoulli distribution. Yes or no, 0, 1, married, single, and so on. So the categorical variables regarding of binary or multi-class generally require some transformation to numerical before feeding them to a machine learning model. Why? Because in the next course we will see that the machine learning model are just functions, and functions cannot handle text, for example. We need to transform, to cast that text in some sort of numerical encoding. And note that some machine learning model do this work by itself, providing some particular tools. For example, in a particular machine learning model, the neural networks, we can look at the embeddings that transform categorical variables into numerical ones. So here we will cover a general introduction to how we can develop statistic tools to analyze data. But this first introduction provides you 2 points of view. We can study a single random variable, a single column by itself, and this is called univariate analysis. Or we can study how 2 or more columns, 2 or more random variables, vary with respect to each other. And this process is called multivariate analysis. Univariate or multivariate analysis are used in a data science project, and generally speaking, in the process of analysis the data, in the first analysis of the data, which is called ADA, the exploratory data analysis. Let's see the first technique we can use, and we will start by the univariate analysis. Of course, if we think about a column as a random variable, we will sure want to know its probability density distribution. Here we will, if not specified, we will always talk about numerical variables. So the best way to understand the data, the column, the random variable, is to describe it by its probability density distribution. But remember, we have only an observed sample, not the entire sample space, the entire population. So we can do it only in approximated way, because the reality in some sort filters the actual properties of the random variables. So the way we approximate the probability density distribution, and we will use the statistical inference, to do so, we will use empirical probability density distributions or probability distribution functions. Let's see some techniques to estimate PDFs. The first and the most used is the histogram. Histograms can be used even for numerical or categorical variables. The kernel density estimation, instead, it's a sort of histogram that is computed using some kernel functions. The core are particular functions. Here you can see the Gaussian functions. These are the kernels. We take a lot of Gaussians and we take the linear combination of them, such that that linear combination will approximate their distribution, the observed sample. So we get an histogram that has a continuous, that is described with a continuous line. That's it. Moving on, we can see another technique, which is the violin plot. The violin plot is nothing particularly strange. It's simply, you can see that's a vertical axis, symmetry axis, and on the left and on the right, you will see the same distribution with a kernel density estimation. Inside, on the axis, you will get some metrics that we will talk about later. For example, the median, the interquantile range, and so on. So other than the approximated distribution, we get other numerical properties. Finally, another way we can estimate the density, the probability distribution of a categorical variable is simply the pie chart. But empirical PDFs can be very useful, but they may provide an overload of information regarding to the complete understanding of the random variables. There's too much information there. For example, in the why we invented the violin plot if we have the KDA, the kernel density estimation, because in the violin plot we add some numbers on it, some pictures. That's why here sometimes it's better to extrapolate to these empirical PDFs some useful properties and just refer to them, or at least as if they are somehow true. For example, when we cannot use empirical PDFs. For example, when we are looking at a random variable that is multidimensional and has more than 2 or 3 dimensions. How can we draw a kernel density estimation in 10 dimensions if we have just a paper? So, since something is something and nothing is nothing, let's extrapolate some properties of our multidimensional variable and just show the numbers or a projection of that numbers. But remember that looking only at its property and the property of the random variable could lead to a poor representation or even a misunderstanding of what the random variable's behavior really is. So if we look at 1, 2, 3 synthetic numbers, these numbers could be true in the observed samples, but false in the real sample space, and also could be misleading of our considerations. We will see some examples later. So let's start. In in the section so before, we've seen we have defined the probability density, the function, and then the expected value and the standard deviation. I will not cover what they are here, but we can define on the probability distribution other properties. For example, the percentile and the alpha order percentile is the value that divides the probability distribution into parts, characterized by the values above and below these thresholds, this alpha order percentile, which is a number. Why we say alpha order? Because the alpha percent of all values will fall between the minimum of the distribution and that number, the alpha order percentile. For example, in here, the 9th percentile, here 3 seconds, means that from 0 to 3 seconds we get the 90% of all the observations, and there's only a 10% left on the right, greater than 3 seconds. The median is another indicator, another statistic we can compute on the sample, and is the value that separates the higher half from the lower half of the probability distribution. So it's basically the 5th percentile. The box plot is a graphical representation of some of these properties. For example, we have the median, we have the 25th percentile and the 75th percentile, which make our interquantile range. We have the minimum that is not the real minimum, but is computed as in this way, using the particular percentile minus the something multiplied by the interquantile range. So the box plot is the second graph that is used in the violin plot. So the violin plot is the concatenation of the box plot and the KDA, the kernel density estimation. Let's recap some random variable properties. We have the mean that we have studied in the statistical inference section. We have the median, the 5th percentile, and we have the mode, or a lot of modes, which are the peaks, the local maxima of the distribution. That's why I say that some function could be multimodal. This is the rastringing function that is a particular multimodal function and is often used to determine the behavior of an optimization algorithm in computer science. For example, let's say we want the optimization algorithm usually wanted to find the bottom, the minimum of this function. But as you can see, since this function is multimodal, it has a lot of local minima. And the algorithm is good when instead of getting itself trapped in a local minima, it gets till the absolute minimum, which is the lowest point the function takes, the lowest value the function takes. Moving on, another random variables properties are the empirical standard deviation that we have studied so far and its properties. Remember that with the standard deviation, you have to be careful to consider the properties we studied during the second section, when we talk about, for example, the Gaussian's properties, in which 3 standard deviations, the range of the median minus the 3 standard deviations and plus 3 standard deviations give us almost all the points inside that distribution, the 99.9% of the points that we can get from the distribution. Remember that in that sigma and in that mu, we refer to the real values of the Gaussian distribution. Here we are doing statistical inference. In fact, here we are not referring to mu, but x bar, the mean, the average, and this is also approximated. Then we have 2 other properties, the kurtosis and the skewness, but I don't want to cover them right now. But why, first of all, I said that looking only at some property from the observed sample could be misleading. Well, for example, let's look at the left-right, top left diagram here. Anomalies. If we have a distribution and for example, this is a sample from a normal distribution, but we get some anomalies. Could be what is called an outlier, or a measurement that went wrong. Someone forgot a zero. Could be anything. But if we compute the mean here, it will for sure shifted from the real mean of the Gaussian distribution. Moving in the middle, if we get a multimodal distribution, for example the average body weight, and we put together the observed samples from the female and the male, it does not make any sense to use the mean average body weight. it can be 30% male and 70% female. What it makes here sense is the mode, since we are looking at a multimodal distribution. And then we have on the top right the long-tailed distribution. Here we have it's called the log normal distribution. So it's a distribution in which it has a fat tail, let's say, or a long tail. So far from the mean and the mode, we get still some relevant probability to happen. So it does not make any sense to use mean for sure, because okay, let's use mode, it's better, or at least median if we have to, but it absolutely makes no sense to use standard deviation and say that from the inequality blah 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 the 99% of the thing should stay between minus 10 standard deviation plus. Makes no sense. First of all, because these are just inferred mean, and what we will get will be inferred mean and standard deviation, what is called empirical standard deviation. But the standard deviation will not get the long tail, the probability that something extreme will happen. So let's not look at it, okay? Moving on to multivariate analysis. The most frequent way to do multivariate analysis is to graph the relationship between the two or more variables. Usually we use 2D graphs, but we can also do 3D plots. That's the same. Here I will present to you 2D graphs only, because we are in a PowerPoint slides. Let's start with two variables. We plot two variables. The first, on the left side, you can see a kernel density distribution of a multivariate variable. We have the sepal length and the sepal width, and we get these two kernels, two distributions. All right, that's fair. And in here we have, let's not look at this, but we have the signal and the time. These are two variables. The signal that varies with time. We can do it using three variables. Of course, using a paper or a 2D plot, we have to abandon. We cannot use three continuous variables. We have at least to introduce one categorical variables, because we can use colors, we can use sizes, we can use a type of markers, a lot of details in the graph that can represent a variable itself. For example, here we have the gender, the fact that the percentage that survived, and the class. Here we are representing three variables. One is numerical and two are categorical. Here we do the same, but we violin plot. As you can see, we have a kernel density estimation, and the violin plot is not symmetric, because in the blue one we are representing the distribution of males, and on the right one, the red one, we represent this distribution only for females. So again, three variables: the total bill, the day of the week, and the gender. We can do it with four variables. So a graph with four variables could be slightly difficult to understand. So you can use it only when doing it, you see a good picture. You can read it. Otherwise, drop it and split it in 2 or 3 or whatever plots. For example, here we have 3 continuous variables, 3 numerical variables, and 1 categorical variable. We have the horsepower against the miles per gallon. We have the dimension of the dot, which represents the weight of the vehicle. And then we have the color that represent the origin of that vehicle. Blue means USA, orange means Japan, and green is Europe. In this sample, for example, you can see that the more powerful cars, vehicles that are considered in this, that are observed, are from USA. Here we get, and they are also the ones that do less miles per gallon. Also, you can see that they weigh a lot. Here the weight is a little bit tricky. I would have used a different scale. The bigger the dot, I would have used the more weight the vehicle has. That's a little bit tricky here. So here there are small plots. This means that the weight is very high. Another technique that can be used in multivariate analysis are the correlation matrices. For example, you can use the Pearson correlation coefficient or the Spearman correlation coefficients that we have not treated in this course. And for example, here you can see the correlation matrix. Of course, the correlation matrix is symmetric, so we do not taking a look to the bottom of the matrix. We don't need to take a look to the top, to the upper triangle here. Also, the diagonal is always equal to 1 since we are taking the correlation coefficients, which is a correlation divided by variance if we look at the same variable. And usually the colors change if the correlation is positive or negative, as you can see here. So we are at the end of the course 5, and we've seen that the probability can be described as a measure onto a sigma algebra. And the sigma algebra is a collection of sets from a space that respects some useful properties about probability. That's what we want. And the elements of the sigma algebra are events, and could be singletons, some sort of single elementary event, or compounds events. For example, if we roll a dice, a compound event could be all the numbers above the value of 3. This is a compound event. With this in mind, we can describe a random phenomena using random variables, and we can associate to them probability distributions. Probability distributions are functions that provide to us at any given point of the sample space the likelihood to see that sample. The true parameter, also the random variables and in particular their probability distributions could have some parameters in them. And there are true parameters in the population in the sample space, but we can almost always not access to that population. We have just a smaller subset, the observed sample. And in order to approximate those true ground truth parameters, we use some tools called estimators, and the estimators are computed using the observed sample. These techniques that came from statistical inference are often used, as we have seen in this last section, as a tool during the ADA process, the exploratory data analysis. So we are at the end of course 5, and we have understand that random phenomena can be scary, but now we know how to deal with them. See you in the next course. Bye.